We started with first order in chapter 2. That looks like a x prime plus p of t x equals q of t. Okay? And then a second order will look a little bit like x double prime plus p of t x prime plus q of t x equals some other function. We have to create some other piece on there. Notice that we are really just extending the same idea outward. Now, one thing that is special about these is that they are monic in the sense that there's a coefficient of 1 in the front. That's a term we use in algebra. Monic means you have a leading coefficient of 1, and that simplifies the slope, the highest slope. But in general, I'll write down this one in blue because it's something that we won't deal with specifically, but it's good to see the pattern. We have the nth coefficient times the nth derivative, and then we step down, third coefficient times the third derivative. Why don't we keep that up here? Plus the second coefficient times the second derivative plus the first coefficient function times the first derivative plus the zeroth, that's still an a naught of t times the x, zeroth derivative, all that is equal to g of t. Now, all of a sudden we have completely different letters. Why? Well, when we solve or reduce down to, this kind of bugged me. Let me write that. I feel more comfortable. Okay. Now, when we write this in a particular order, you'll notice that the black ones are again monic. The leading term is a 1. And that's something that we do to make the form of the solution as unique as possible. So in general, you could keep multiplying this whole equation by any number and it would change all the coefficients slightly. So to keep it as unique as possible, we scale by that leading coefficient. But in doing so, we actually change slightly the way that the equation works and how it looks. So I want to keep that in mind. One other thing to think about is that this sum is a linear combination. In fact, you can write it as the row vector or very wide matrix an of t, then a sub n minus 1 of t, and so on down to, I'll just erase that, we didn't actually write that one down, dot dot dot, a3 of t, a2 of t, a1 of t, a0 of t, almost forgot that one. That's our 1 by n plus 1 matrix. And then we multiply by the nth derivative on down to the third derivative, second derivative, first derivative, and then the zeroth derivative or function. That gives us a dot product of these two vectors, which yield a single scalar, but in our differential equation world, that is not a number, that's a function. So that's kind of the linear algebra perspective. You can think of it kind of like a dot product of two vectors. The vectors of the coefficient functions and the vector of the unknowns. The function, derivative, second derivative, third derivative, all the way up. Those are all the unknown components. And that's why we think of this as a standard form, because we're really thinking of it as ax equals b, right? You have a, the coefficient matrix, x, the vector of all the unknowns, b, the known quantities. So that's why we call this thing the standard form. We move all the x's onto one side, all the unknowns onto one side, and leave the functions of t on the right-hand side. It's just matching ax equals b. Kind of crazy. Standard form. Okay. So let's see. That's all about our perspective. Again, I told you we're not going to go this deep. We're going to stick mostly with second order, but I just want to show you a little bit about how it can expand out. We'll do a couple of third and fourth order, just for fun. There are some applications where we actually need them, so we'll see. Okay, so there's a couple more key ideas that we need when we jump into differential equations. The first is the idea of I just erased it. Is the idea of existence of solutions. And this is one thing that you can identify from the monic form of the differential equation. So I'll write this out. If all coefficient functions in the scaled linear form, that would be something like P of t, Q of t, or just P of t in the first order form, are continuous in a given interval going from time 1 to time 2, which includes the initial condition. Often we'll have initial condition at t equals 0, but sometimes it's at a different place. Then the solution to the differential equation exists and is unique for t between t1 and t2. This right here is the existence and uniqueness theorem 3.2. So I'll write that up here. Whoa. The existence and uniqueness of solutions theorem. Now, a quick example of this would be something like 1 minus t squared x double prime minus 2tx prime plus tangent of tx equals 0 with x sub 0 equals x naught. So we know what time we're looking for. We want to find the largest possible range, largest possible interval for the domain of this function. So the first thing we need to do is divide by the 1 minus t squared. Because without a monic form, a leading coefficient of 1, we don't actually have all the conditions. So now let's look for continuity. The t is fine, but the 1 minus t squared has some problems. So let's draw our time. Here is 0. And what values of t blow up here? Well, when t is equal to 1, certainly. So let's knock out t equals 1. And then when t equals minus 1, it also knocks out. So I'll go over t equals minus 1. Okay, so we know that the interval of solution can be no bigger than negative 1 to 1. But let's see if there's any more restrictive conditions. What about tangent? Tangent is equal to sine over cosine. And cosine is equal to 0 at various values. Tangent also blows up. But where are those values? Pi over 2, negative pi over 2, 3 pi over 2. Actually, it's pi over 2 plus multiples of pi, right? So let's see. Are they within that interval? Well, pi over 2, that's 3.14 roughly divided by 2. That's about 1.56. It's certainly bigger than 1, right? Somewhere over here, we got pi over 2. And the next one would be pi below that is another one over here at negative pi over 2. Okay, so we know that the biggest interval over which this differential equation has a solution, largest interval for solution with x sub 0 equals x naught is negative 1 to 1, or t between negative 1 less than t less than 1. So that is the largest interval. And over that interval, we know by theorem 3.2 that the solution exists in that interval and is unique. Now, what's interesting is that if you were to graph the differential equation, there are also solutions that pop up in this interval, and solutions that pop over in this interval, and again, and again, and again. So there are multiple solutions that pop up in different intervals. So this uniqueness theorem only applies to the interval around our initial condition. If we have a different initial condition, we get a different interval, and we get a different solution. That's a little crazy. Now it'll look pretty similar. It's based on the same integration techniques, but it'll be a different solution based in that interval. So kind of crazy. So that's one of the key things, is make sure that we do scale by 1 so that we know where the points of discontinuity are.